Justin will want to watch this as well. So we're going to do today's lesson. We'll get as far as we can. I have found the next lesson you're going to watch over the weekend. Okay, and it goes for 45 minutes. And you're just going to watch it on YouTube and write down the notes as a normal lesson. That way we claw back one lesson. And then I give homework every year, and the homework is to watch the Manhattan Project, which it's up there as that one. For some reason they've put it into 5 parts and they go for 10 minutes, but it hasn't been brought down for copyright. It's still there. I don't know why it's in 5 parts. Occasionally I find documentaries for my students to watch, and then one year it's been removed due to certain copyright issues. But it's still there. So we're now looking at fission and fusion and bombs and nuclear power, but they all involve the same concept of mass defect. If you can take something and split it apart into smaller fragments, they're going to be lighter. There is missing mass. That missing mass has been converted into energy. Again, that's what Einstein figured out. So we said fission, on that previous curve, the binding energy per nucleus curve, if we can split apart large atoms into smaller atoms, we can release kinetic energy. Justin, just there. And I'll give you your 15 minutes. Thank you, Justin. You can start. Now, here is the problem. Not all fragments will undergo fission. Now, they're just sitting there. If they're unstable, if you're a heavy isotope and you're unstable, you can release energy in a few ways. Alpha particles, so anything above bismuth, which is atomic number 63 or 83, I can't remember, it'll spit out an alpha particle, Scott, or it can spit out a beta particle, okay? But then, here's the next thing. You can bombard objects with neutrons. So when they figured out a way to fire neutrons at samples, physicists went crazy. They found every single isotope they could, and they said, all right, let's just blast it with neutrons and see what happens. Now, neutrons, remember, they are not ionizing, they are neutral, but they can get captured. So if you fire a neutron into a nucleus, if it gets captured, all of a sudden, you might have increased the ratio of neutrons to protons. Sometimes it does nothing. Sometimes the ratio is still happy. And so it just goes, yep, thank you very much. I'm now a heavier isotope of that atom. Oh, I lost my train of thought. Often though, if it has too many neutrons, it will then become a beta negative emitter. So it's called neutron capture. That's why neutrons have a quality factor. If I blast you with a neutron beam, some of your atoms will collect those neutrons and then become unstable. So it's kind of like a two-step process, okay? It's not really it's not ionizing, but it can still damage you via this neutron capture. So they went about doing that, and they noticed, oh, that's great, we made heavier isotopes, and then they were able to actually make transuranic elements. Before 1943, there were 92 naturally occurring elements on Earth, and that was it. And then in 1943, they actually managed to go beyond element number 92. They made element number 93, Neptunium, and element number 94, Plutonium. Keeping in line with the naming, they kept naming them after Roman gods. Not planets, Roman gods. Uranium was Uranus, then Neptune, then Pluto. These are Roman gods. They are not planets. Planets were also named after Roman gods. Let's get into this. As I said, very similar to binding energy calculations. I'm going to stop the story here because we're going to get to how fission was actually discovered. So, we want to have an equation. There will always be a mark for writing out your equation. This is not in the data sheet, but you have to show some sort of process of forming an equation. So we'll say mass defect equals. Now we're going to say I'm jumping the gun here, but I'm just going to write this above here and go, just wait until I figure out what I'm doing. We've got a neutron plus an atom that is said to be fissile. Then it's going to split apart into the fragments. Okay? Now, it's going to vary. Mass of fragments. Okay? So in the late 30s, early 40s, they had this new device that could process that they could make neutrons and fire them at things and then figure out what was happening. They said, all right, neutron capture, sometimes it becomes a beta emitter and it just basically goes, spits out a beta particle, turns a neutron into a proton, and that atom is healthy and happy. They got through that torture. But then they started firing them at heavy atoms. And all of a sudden, obviously they're measuring the beta with a Geiger counter, right? So that beta particle that was emitted, they would be able to measure. But all of a sudden, in the early 40s, it was actually German physicists that found that when they fired a neutron at uranium, that the activity went crazy. The Geiger counter just went like lots of activity. One neutron, lots of activity. They're like, what the heck's going on here? We're suddenly releasing all this energy. They didn't quite know what was going on. Now, here's the problem. Shh. Spencer, stop. World War II was going on at the time, and so there was no communication. Before then and now, we communicate. We publish our findings. Look what I discovered over here in America. Look what I discovered here in England. When the war started, there was no communication. So this was going on in Germany. They may have found the processes to make the atomic bomb. But obviously the story behind it is that a scientist found out before the Germans did, and that's what the Americans went about making atomic bombs. But let's get back to what's happening. So the neutron came in, and it was captured, but rather than just spitting out a beta negative particle and we're done with it, what happens is it basically captures it, and for, like, we're talking like a nanosecond, it's unstable, and it basically rips apart, okay, into two big fragments. Always two big fragments, never three, never four, always too big. But sometimes a couple of neutrons. We'll talk about that in a moment. Have a look at this. Mass number of fission fragments versus percentage yield. There is a more likely combination. Mass number 93 and 137. So that could be, I don't know, barium and krypton. All right? But that's not always going to happen. It's completely random. You can't say that if I fire a neutron into this uranium atom, it's going to split into that and that. You could say that there's a 10% probability that I'll get that. But you could just as likely get him and him over here. Or him and him. Down here, oops, try again. That would be two equal-sized fission fragments. Down here, 118. Again, it's unlikely that that occurs. So this is just an empirical curve that shows there's there is around 40 different fission fragments. I'd like my best try of drawing. No. Let's try again. Yeah, there we go. That's all right. So here is my... Whoops. I'm going to draw my little fissile nucleus.
What's a fissile?
I'm glad you asked. Okay, so there are two words. Fissile and fissionable. Lots of things are fissionable. But if you have a low probability of ripping apart, then we call them fissionable. It's been observed, but it's unlikely. If something's fissile, it just rips apart like that. And so lots of heavy isotopes are fissionable. It's been observed in a lab occasionally that we break apart. But there aren't too many fissile nuclei. There's a couple of good ones. ones that we can use. Okay, uranium and plutonium and thorium. In fact, there's about 3 fissile, which means that they will readily rip apart rather than sometimes. Yes?
When in the equation when it's massive neutrons, do you only ever fire 1 neutron?
Okay, so yeah, this is my fissile nucleus. Okay, so could we just quickly describe him as fissile nucleus? Okay, and here is my neutron. Okay, so in comes flying my neutron. And by the way, there are animations that show this process. It will be in that documentary that I want you to watch over the weekend. So in comes my neutron. And then what happens is it's unstable, and we're talking about less than a nanosecond that it's captured that, and it goes, you know what, I don't like this, and it goes, and it splits into 2, as I said, always 2 large fragments. Is that, let me make it a little bit smaller for conservation of mass. Okay. Now, again, for some strange reason that's not quite known, a couple of neutrons go flying out as well. The neutrons that were originally sitting there in the atom, minding their own business, they don't go into the fission fragments. They might be flung out. And again, it's random. That's a big neutron. Sometimes it's 2, sometimes it's 3. Okay? So that's why we have to make sure when we do our nuclear equation that we're balancing the books. You've got to make sure the mass numbers are balanced, and you've got to make sure that the atomic numbers are balanced. Justin, you have 5 minutes left. Thank you. Now here is the important thing. For fission to occur in uranium-239, oh my gosh, I just had a mental blank. 235, my bad, 235. It has to be called a slow neutron. This is the funny thing. Trent, hold out your fist. All right, this is an atom of uranium-235, and it's said to be fissile because it will capture a neutron and readily split. Hold out your fist. That's something else. It's fissionable, that it could capture a neutron, and occasionally it goes, you know what, I don't like this, go back. Now, if my neutron that comes flying out is too fast, it will keep going straight through. Okay, it can literally be so fast that it goes through the nucleus and out the other side before it can be captured. So it has to be slow. Now, slow neutron literally refers to how fast it's travelling. Okay, and so we're on the order of 1 to 100 keV. We've got to slow it down. So often when neutrons are spat out, they're too fast. But if I can slow my neutron down, that was embarrassing. If I can have a slow neutron, it will spend more time in the nucleus and have a greater chance of being captured and then split apart. So we have to slow them down, and it will immediately undergo fission. So, items that can undergo fission readily or frequently. Okay, but we're not going to care about fissionable. That's just, we don't care about fissionable. There's no use for that. We want the fissile stuff. Okay, now I'm going to have a quick little story time here. During the 1930s, Hugo, if you were a Jewish scientist in Europe, it was not good. In Germany, even worse. Lots of Jewish scientists fled Germany during the 1930s, and many of them immigrated over to America. Rather than just going to Poland or Switzerland or France or or Austria or Italy. No, it's too dangerous there. They got up and they left. There were many famous ones, Albert Einstein, Leo Szilard, it's not Seaborg. There were many Jewish physicists that fled, okay? And they went to America. And that's probably one of the reasons why the Allied forces won the war, because they had these smart physicists that were able to help develop the atomic bomb, okay? 2 minutes left, Justin. Now, there was a physicist called Leo Szilard. It was S-Z-I-L-A-R-D. He was a Jewish-German physicist who fled to America, and it was he that actually saw other German physicists had discovered this process of splitting apart the nucleus. And so he went, holy crap, this is bad. If they get enough of these atoms together, they could release this energy all at once and make a bomb. So he buddied up with Albert Einstein. He went and spoke to Albert Einstein and said, look, this is what I've determined, blah, blah, blah. Albert checked the maths. He said, you know what, you're right. Albert Einstein was a bit of a pop royalty at the time. Like, he was like, you know, the Brian Cox and the black mustache science guy. Neil deGrasse Tyson, you know, he was a celebrity. So he had a bit of gravitas. So he wrote a letter to the president, I believe, Roosevelt at the time, and basically said, we need lots of money to get this uranium. All done? Thank you very much. Oh, I'm going to have to print out. Hang on, I might have a spare one for you. And so it was actually a letter sent to President Roosevelt saying, from Albert Einstein, saying, we need to build this bomb. Okay. Now, Leo Szilard was doing experiments with uranium, and he actually came about slow neutrons by accident. He was basically bombarding heavy atoms, so all of the very heavy, you know, above lead metal atoms, with neutrons, and monitoring with Geiger counters the activity. And then, just by accident, he happened to place, Hugo, some paraffin wax. Don't ask me what he was using paraffin wax for in the 1940s. I'm sure there was some use. He just happened to place down some paraffin wax between the source of neutrons and the source of uranium. And the Geiger counter went like crazy. All right? The paraffin wax was causing more fission to occur in his little sample. Okay? So what was happening is that the paraffin was actually slowing the neutrons down. The neutrons that he was firing were too fast, and lots of them were not being captured. He slowed them down accidentally, and then all of a sudden, all the slow-moving neutrons caused this fission. Now, I need to quickly scroll. Why was the Geiger counter going crazy? The reason was, if you are uranium-235, you have a large ratio of neutrons. Remember that graph? No, don't remember. Cite it. This graph here. Okay? So you're way up the top here at uranium. You need to have a huge ratio of neutrons to protons. Let's have a think. Uranium-92, that's 92 protons. How many neutrons? 235, take 92, 140 something. So 92 to 140, that's a ratio of like 1 to 5, okay? Let's just round it crudely. 1 to 5 ratio. You split that apart, and now you say, all right, you are now a smaller fragment. Let's say that you're 120 and 120. But you now still have that 1 to 5 ratio. But if you are an atom that has mass number 120, you don't want to have that ratio. You're coming closer to this line, the 1 to 1 ratio. So a 1 to 5 ratio for you is far too much. And we learned right at the start that if you have too many neutrons, you are going to spit out beta negative. But not just one, because you are so far from the zone of stability. You are so far from stable isotopes. Remember, like the machine gun kind of analogy. You are going to fire out beta, 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 beta. You might have to spit out 10 beta particles, transmutating, 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 until you finally become stable. And so that's why the Geiger counters lit up like crazy. They were detecting not the event of fission, but all of the fragments this causes the fission fragments to be what? What are they emitting? What type of radiation was I just talking about? Beta negative. Okay? So that's the problem with fission. Fission's great. I mean, it makes a lot of energy, and we can get a lot of energy from nuclear power plants. But the problem is that the fragments, the spent fuel, is going to be highly unstable. And remember I said that if you're that far from the zone of stability, it might be like a machine gun spray of beta particles. But then once you get closer to the line, sometimes you can have a long half-life. So maybe when you're there, you might have a half-life of 20 or 30 years or 100 years. So that's the problem. Your fragments have their beta emitters, and we'll just write here often with long half-lives. Okay? Now I know I've skipped a bit, but we will make sure that we fill in the previous page before we depart. We will talk more. This is the main problem with nuclear power at the moment. You can get lots of power, but what do you do with the waste? It's going to be highly radioactive, emitting beta negative particles for decades. So you need to store it somewhere for hundreds of years before it's finally decayed down to stable, and then you can go and throw it in the oceans and rivers. Someone else's problem. Okay? So let's get back to mass defect. So here is a common event. Okay? So remember we said there are around 40 different pairs of fission fragments. This is one of the pairs, barium and krypton. So, before we calculate the energy, we have to do our nuclear equation, making sure that our mass numbers are balanced and our atomic numbers are balanced. So, uranium-235 plus a neutron, remember that's the one that gets captured, is going to go to barium. Now I think barium was 56 because I just marked your barium prax. Krypton 91.
36.
Thank you. Plus, now, here's what you're going to do for every fission reaction. You're just going to write a neutron here.
That's potassium.
Oh, sorry, we need an R there. Okay, this is what you're going to do. Often the easiest question, and you're going to get one of these, is you're not told how many neutrons are ejected, but you're told what the fission fragment pair is. So you write it down, but it's not yet balanced, because if I try to balance my mass numbers, well, hang on, let's balance our atomic numbers first. 92 and 0, it's balanced, okay? I know. You're 2 minutes ahead of everyone. Okay, so if we just check, we had 92 protons on that side. We've got 92 protons on that side. Balanced, good. But, and you're told, we know the answer's 3, but imagine it didn't say that. You have to figure out how many neutrons are sprayed out. So, we'll check. Oh, that's not what we require. We've got 236. Currently, we've got 233. So obviously, yes, we're missing 3. Okay? We are missing 3 mass number. Matthew, are you okay?
Yeah.
All right. And so remember, we have to conserve mass. Mass just doesn't disappear. So we can't just say, well, those 3 neutrons just disappeared into the ether. They are still there. They went flying out. And remember, right at the start of this topic, you cannot write this. Do not write this. Well, you're not going to, because that is not how matter clumps together. You cannot get 3 neutrons clumping together with 0 protons. That's not how we do it. It's like mathematics. We need a coefficient out the front. Okay? And so now, with our 3 neutrons, we can say that our mass number is balanced. Okay? So this is what you'll need to do in most questions. You will have to firstly balance. You draw a balanced nuclear equation. You need to determine how many neutrons are released. So this is one of those reactions or events where 3. And so we said sometimes 2, sometimes 1, sometimes 4, but generally it's between 2 and 3 are released in an event. Okay? Again, we don't even know what isotope of krypton and barium it might be. If it was a smaller isotope, then maybe an extra neutron is ejected. But on average, you're expecting around 2, 3, or 4. Okay? All right, now, let's do the energy. So this is where we need to determine the mass defect. So I'm going to write my equation. Mass defect equals and so for this reaction or event to be sort of exothermic, releasing energy, we need this to be heavier and this to be lighter. Again, look, you are given a box with all of the masses present. So, again, we are now going to write in our 1.008 664 plus 235.043923 minus, and here's where we need to be careful. We've got lots of numbers here. We've got krypton is 90.92345, and then barium is 141.916453, and now 3, and I'll highlight that because again this is a common mistake that students make. They just go, plus a neutron. No, there were 3. Their masses must be considered. Some students are tempted to simplify this by removing the neutron over here and dropping that one down by 2. Please don't do that. Get into the habit of saying, how much mass have I got at the start and how much mass have I got at the end? Okay? So, you can check this at home. I'm fairly sure I haven't made any mistakes. You get a mass defect of 0.186692 atomic mass units. What? What'd you get?
Yeah.
0.1867.
I got 6746.
Oh yeah, that's fine.
All right.
Okay.
Times by 931.
Yeah, 174.
Cool. All right. So, we did the balanced equation at the top. That, if we look at the energy, that is huge. An alpha emission will release about 5. A beta particle emission will release 0.1 to 0.9. This is 174. A chemical reaction, so one molecule of ethanol reacting with 6 molecules of oxygen, that's releasing on the order of 10 or 20 eV. This is 174 million. So we are talking 10 million times more energy per mass due to a nuclear reaction rather than an electron reaction. Chemical reactions are just electrons jumping around. This is releasing energy from within the nucleus, that binding energy being released. There is a rule of thumb. As I said, there aren't too many nuclear reactions you can get. There are 40 pairs, and most of them are more probable than the others. You're going to get around 150 to 300 MeV. So could we just have a rule of thumb that you're looking for a number that's around about 200? In fact, I'll put this down. Okay. So this is a good way. If you stuff up, let's say, William, that I forgot to include my 3 neutrons. Oh dear. So when I did my mass defect wasn't 0.18, it was 3.18. And you're writing it down. Oh, cool. Thank you, calculator. 3.18, blah, 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 blah. Then you times that number by 931, and you get 3,900 MeV. Thank you very much, calculator. Answer equals 3,000. No. All right. And same, the opposite. Let's say you stuff up and leave out a 0. And then your mass defect is like 0.0018, which is, small. We've done small mass defects before. Times by 931, and you get 1.74 MeV. No, that's too small. You're in the order of 100, 200, 300 MeV. If you get that number, there's a fairly good chance you got the answer correct. Yeah? Because you've been given the values. You've been given the numbers. And so if you forget 1 neutron, your answer is going to be out by 900. All right? So, 95% confidence, if you get a number around that, you know you've got the right answer. Yes? Yes, you may. So, do you want to just jump to question 11, please? I'd like you to have a go at this before you all depart for the weekend. Because I don't see you tomorrow. Okay? Page 11. There are 2 fission events, I believe. 1 and 2. So guys, this I probably copied and pasted this from a past test. This is the kind of question that you get. You'll be given the masses, you'll be asked to write the equation, find the mass defect, find the energy release. That's a standard question. So, you need your periodic table, because you don't know the atomic numbers, so you have to get your periodic table out. Yeah? Who has not got a periodic table? Did you not get one of these at the start of the year? No, you started about 2 days late. These are blank pieces. Does anyone want a data sheet? They have misplaced theirs.
I've got one, sir.
Thank you, Hugo. Oh, I'm all out. I'm all out. No, I'm not. Hang on, I've got a data sheet here. Stephen. Again, guys, this might be worth maybe 6 or 7 marks. Question? Well, so one event means one fissile atom, one fissile nuclei splitting. So we're just going to look at one. So you've got to basically find the mass defect of that nuclear equation. Okay. Don't forget that you have to accept or capture a neutron. Alright, so that neutron isn't even mentioned it doesn't say that a neutron is captured by, it just says this happens. So you can write out the template, but then you've got to go to your periodic table to figure out the charges. In fact, you don't need your periodic table to figure out the number of neutrons.
Oh.
We know that these two have to add up to 92, but you have to find it in the periodic table. So somebody want to help me out and tell me what cesium is? 55, thank you. And then this guy has to be what? 43. What? Sure, I believe you. 37. So what do we got? We got 236. We've currently got 234. Okay. Are we all happy with that? We need to have 2 neutrons so that we have 236 nucleons on the right-hand side. Because we had 236 nucleons on the left-hand side. There will still be students that get this wrong, no matter how many examples we go through. Where? Are you already onto the... Oh my gosh, you work too quickly. Tap the brakes, buddy. Oh, hang on. In fact, I don't think I have the work solutions. So how about you tell me... Oh, actually, let me just write it out in full first.
Is it just 3 significant figures for the mass?
Well, no, it's add and subtract, so you use the decimal place rule.
Okay.
Yeah?
Yeah. 0. Wait. I meant, hang on. Sorry, binding energy.
Well, you multiplied by a 3 sig fig. So now your binding energy is 3 sig fig. Yep.
That's not 3 sig fig.
Seriously? 3 sig fig?
Mm-hmm.
Whatever the 3 sig fig is about.
Well, that's the problem. You could probably find a physics website that has the mass energy equivalence in MeV to 7 sig fig. It might be 931.478 blah blah. In which case you can keep the precision, but. Okay, would you mind telling me the mass defect?
0.193219.
Sure.
Is it 3171?
I got 3171.
Yeah. So it's 0.19.
Yep.
Sorry, my calculator's
3171.
Yeah, I got 0.194427.
Were you wrong?
Well,
That number.
I don't know. I don't believe I've worked this question before, so I'm relying on you lot.
The binding edge is very round.
Huh?
So that's correct.
Okay.
It gives you 180 MeV.
I got 190.
Is that 3 sig fig?
Yes. Well, I'm assuming.
Well,
It's
do you
179.
say 1.80 times 10 to the 2?
Yeah. Okay. So yeah, at the end, remember, we are always now multiplying by a number in our data sheet that is 3 significant figures. So we need to multiply by, express our answer to 3
Yeah. My bad. I'll write it again.
Oh, well,
Nick, what did you do?
I mean, I might pick a fission fraction again, whereas energy release is.
Hold on, is it N capital one or lowercase
And
one?
I don't want you going, oh, I've got a problem. And sometimes there might be a fission fragment that only spits out 110. So, yeah, 100 to 300. That's good. Please do the next question, yes. Move on to the next question if you are done.
Yeah, what's 10 and...
SN.
50.
I know
One, two, three.
Oh, U233. Fair enough. I didn't think that was... Maybe it's fissionable. Oh no, it says common, so it must be fissile.
Would you agree that 1.20? Yeah. Would you agree that thorium looks like bonium? No. Bonum.
What do you get up to?
Alright, what are we up? Oh, 4!
4 whole neutrons. Also, sir, it should be down there.
I know. I know.
I could train you through that, but that's currently considered to be child use nowadays.
Atomic number of molybdenum.
54, sorry, 42.
Thanks a lot. 42.
No. Oh, yeah, sorry.
And 50.
50.
10 is 50.
Is that
Alright.
actually a bomb? Like, is that element actually called bomb?
No, it's molybdenum. Oh, that one. That's boring. It just looks like bonium.
What does this equal make?
Okay.
I don't want to tap it. It's magnetic.
I did it. You can do it too. You're a big boy. You got
Please, buddy.
No.
I need it.
You're a big boy. You
This
did
is
it.
gonna take forever.
Exactly. You didn't do it right. Did you do? Did you do 4 neutrons?
Oh, that's uranium 23. Try that again. 233.
You didn't put the times in. You didn't put times in. Oh, wait. What? No. What have you done? Check all your decimal places.
Working in radians?
Yes.
We done the second.
Yes.
Mass,
179.
what's the mass defect?
0.192362.
Thank you.
And it gives 179 mega electron.
I just got it. Nick.
179.
Oh, what? Hold on. Oh, Nick, your calculator's wrong. It's 0.112.
I rounded it differently than you.
Alright, check. I mean, I'll say if 3 or 4 people agree on the number, then it's probably right.
I mean, either way, it's going to be 179 mega. It's just like how you. Yes, I calculated around.
Okay. Spencer, Bergsma, Gamble, did we get these 2 questions done? Yes, no, maybe? Alright.
On that side, so that side, the neutral should be the same. They should both 1 on the top, 0 on the bottom. On the left,
Look at the
0
board.
0 1.
No. Shush. We started off. Let's just make it round, nice round number. We started off with 234.0.
Because otherwise, you have these two ones
4.
going all the way up to the left.
And then something happens. Now we have 234.03. If you weigh the mass, all the
This is evidently made before they've been made.
Einstein says that ABC mass has to be
Let's look up.
matter and energy are simply manifestations of the same
I know
thing.
that one's organization.
You can make energy
One
with
of them's
matter and you can make matter with energy. What we've done here is we make energy from matter. That's energy, E equals. E equals mass defect times 1 Yes.
Oh god.
Moscovium, Tennessee, We're going to Tennessee. We're going to Tennessee.
Is Tennessee the place?
One of them. Year 11s, just before I let you depart, please listen up. Listen closely. Listen closely, please. Yes. I am going to send... Shh. Right. I'm going to send you an email. It's going to have a couple of links. I'd like you to watch this 50-minute documentary on the Manhattan Project, which is an effort that the Americans, the Allies, went to getting enough fissile material that they could make a bomb that basically ended World War II. It goes for 50 minutes. Okay. Next, in this tab, we are good for 2 lessons. Well, we've just done lesson number 7. That will be. I'll upload that later on this afternoon. But lesson number 8, you're going to have to watch over the weekend. And in that lesson, it's going to pretty much complete all of the information on fusion. So if you go beyond, it'll be sort of from page 16, so we'll finish this booklet before the test. But the video you're going to watch, lesson number 8, is going to cover sort of pages 16, 17, 18, 19 and 20. Okay? So I'll send that to you. But you've got 4 nights to do it. You've got 4 days, because I do not see you tomorrow, so you need to get it done. Because I'm just going to carry on as though you've covered that lesson. If you don't watch that lesson, it's like you were absent today, and you've just gone into the test without doing anything. Okay? So please make sure, I apologise that I'm forcing you to learn or do more lessons than is timetable, but we need to have that lesson. Okay? Question, Hugo?
You answered, sir.
Okay. Alright guys, so I'll send you that email later on this afternoon. See you later.
Exactly. Email
See you.
for the lessons.